Okay, myself Goutham and I teach EDC at Home Institute, Hyderabad. I've been teaching EDC for the last 5-6 years without much complaint, and I also know a bit of analog circuits. But today I'm here to discuss a problem on semiconductors, which you can see is related to what photo generation of EHPs and also the recombination of excess minority carriers and the resulting excess minority carrier concentration profile. In fact, this question you must be knowing that it has come up in the recently conducted GATE exam in the EC paper. A few students were asking me what the answer is to this question. The answer that I got is what? 1.01. In fact, to be precise, I got this value 1.01139. So I think even if you had marked 1, you should be getting 2 marks. See, in this video, I won't provide the complete solution as to how I arrive at this answer. Once the official key is out, then I will put up the complete solution. But what I will try to do in this video is to give you a bit of insight into what really happens inside this semiconductor, okay, when it is subject to what generation, and then you have this recombination profile and so on. First of all, what is given? We have a p-type semiconductor which lies between -2 ln and +2 ln. And this p-type semiconductor is at steady state, okay. Again, steady state, it means what? You take any location, at that location the values of n and p will not change with time. You see, the values of n and p, they can vary with distance, but at any given location the values of n and p will remain constant with respect to time. That means what? There can be a spatial variation, but there cannot be any time variation. That is the meaning of steady state. Another keyword that I can see is what? Low level injection. That means the excess carriers produced are very small in number compared to the existing thermal equilibrium majority carriers, okay. And 2 boundary conditions are also given. What are the 2 boundary conditions? Excess minority carrier density or concentration is 0 at x equal to plus or minus 2 ln. What are these plus or minus 2 ln? Are they not the 2 ends of the semiconductor? So at the 2 ends of the semiconductor, the excess minority carrier concentration, they are saying it becomes 0. I mean, it should become 0. Because when you reach the surface, we have a discontinuity. And this will lead to what? Creation of a lot of surface states, which will greatly enhance the rate of recombination. You know, the surface recombination velocity will be very high and so on. So due to the high surface recombination velocity, at the surface, always the excess minority carriers, if at all they are present, they will immediately recombine, so that the excess minority carrier concentration at the surface always becomes 0. And here also we have the same thing, nothing surprising. Even the diffusion length of electrons is given. How much? 10 power minus 4 centimeters, which is 1 micron, okay. Profiles of photo generation rate, that is what this graph, and the recombination rate of excess minority carriers are shown. So this is what? G, this one is what? R. So given these things, the question is what? To find the magnitude of the current density due to the photo generated or the excess electrons at x equal to plus 2 ln. So that is what? At the right end of the semiconductor, what is the electron current density, okay. So first of all, do you have generation of carriers or photo generation of carriers throughout the semiconductor? No. We only have photo generation of carriers between minus ln and plus ln, and in this region J is what? Uniform or constant and equal to what? 10 to the 20 per cm cube per second. But if you look at the rate of recombination of excess minority carriers between minus ln and plus ln, it is not uniform. It kind of exponentially decays as you go away from x equal to 0, either to the right or to the left. And the other thing you can notice is what? Outside this middle region between what? Minus ln and plus ln, both g and r are equal to what? 0. That means from ln to 2ln and also from minus ln to minus 2ln, g minus r are the net generation rate. It is what? 0. No generation, no recombination. So these two regions on either side of the p-type semiconductor, that is what? Ln to 2ln and minus ln to minus 2ln, are they not similar to the base region of a bipolar junction transistor? Even in the base, which is what? Narrow or very narrow compared to the diffusion length of the minority carriers, there will be no recombination. Of course, there is no generation. So the minority carrier concentration profile in the base, would it not be linear? In fact, as you go from emitter to collector through the base, always the minority carrier concentration or the excess minority carrier concentration, it will linearly decrease as you go from emitter to collector through the base. So in these two regions as well, that is what? Ln to 2ln and minus ln to minus 2ln, we would expect a similar thing to happen. That is what? A linear profile for the excess minority carriers. Okay. First, let us write what is G minus R in between minus ln and plus ln. Okay. In fact, first I'll write minus ln less than x less than ln. What is G minus R? G is what? Constant and equal to what? 10 to the 20. R is what? Exponentially varying. It is equal to what? 10 power 20 times e power minus mod x by ln. In fact, let us try to plot how this G minus R varies with distance. When you go from minus 2ln up to plus 2ln, look at this. This is what? G minus R. This is what? X. Let this be ln. Then this would be minus ln. This is what? 2ln. This would be minus 2ln. Okay. So outside this middle region, because both G and R are equal to what? 0, even G minus R would be equal to what? 0. 0. This is also 0. Now first look at this segment between 0 and ln. Between 0 and ln, x, is it not positive? If x is what? Positive, mod x will be equal to what? X. So that G minus R would be equal to what? 10 power 20 minus 10 power 20 times e power minus x by ln. This is for x lying between 0 and ln. Okay. We can also write this as 10 power 20 times 1 minus e power minus x by ln. In fact, if you look at this expression, is it not similar to how the voltage varies with time in an RC circuit where the cap is getting charged? So there also the voltage across the cap, starting from initial value, it will exponentially go towards its final value. So here also we have a similar thing. Okay. So at x equal to 0, what is R? It is 10 to the 20. G anyway is what? 10 to the 20. Difference is what? 0. So from 0 to ln, G minus R, it would exponentially increase. Okay. And then because for x greater than ln, G minus R is what? 0. At x equal to ln, this G minus R would abruptly fall to what? 0. Thereafter it remains at 0. Again, because of symmetry and so on, you will have a similar thing even to the left of x equal to 0. Yes, you will have something like this, and this will also fall to what? 0. So this is how the net generation rate varies with distance along the length of the semiconductor. Okay. I already told you in this region and in this region, because there is no generation, there is no recombination, the minority carrier concentration profile or the excess minority carrier concentration profile, it would be linear. Okay. In fact, I can make a rough sketch of the excess minority carrier concentration profile for these two regions. Okay, to start with, what is given in the question that at both the ends of the semiconductor, the excess minority carrier concentration, it is what, 0. So at x equal to 2 ln, it is what, 0. At x equal to minus 2 ln as well, it is what, 0. So this red color is what, for G minus R. Pink color, it is for how the excess minority carrier concentration varies with distance. Okay. You see, if you look at the red color graph, G minus R at x equal to ln and also at x equal to minus ln, is it not maximum? Whereas here it is what, 0. G minus R is what, 0. But here G minus R is what, maximum. So you would expect that at x equal to ln, you are going to have a good number of excess minority carriers. And we already know that in this region, the minority carrier concentration varies linearly with distance. Okay. So here, let's say you got this many number of excess minority carriers. Again, because of symmetry, even at x equal to minus ln, you're going to have the same number of excess minority carriers. Let me slightly pull it down. So at both x equal to ln and x equal to minus ln, the number of excess minority carriers would be same, per unit volume and so on. Now in this region, you know the variation is going to be linear. Variation linear, it means what? Just join the 2 points with a straight line. Okay. So between ln and 2ln, the excess minority carrier concentration will linearly decrease, whereas between minus 2ln and minus ln, the excess minority carrier concentration would linearly increase. Now go back to the question. Find the magnitude of the current density due to the photo generated electrons at x equal to plus 2 ln. In fact, this electron current density, is it not the electron diffusion current density? Because always we tend to neglect drift of excess minority carriers, because excess minority carriers are very, very small in number, and even the resulting electric field, if at all it is there, is going to be too small to result in any significant drift current. So whatever electron current you have, that is entirely going to be diffusion current. Okay. So Jn diff is equal to what? Q dn dou n by dou x, where at x equal to, at x equal to 2 ln. So all you have to do is to find the slope of the excess minority carrier concentration profile at x equal to 2 ln. But already we know that between ln and 2 ln, we are going to have a linear profile for the excess minority carrier concentration. So it's dou n by dou x at x equal to 2 ln is nothing but the slope of this straight line. So this problem is all about finding the slope of this straight line. Okay. In fact, this thing is nothing but m. So if you can manage to find m, you will get the required current at x equal to what? 2 ln. Now from G minus R, how do you proceed? See, you have to start with the continuity equation. What is that continuity equation for minority carriers? Is it not this thing? Dou n by dou t is equal to what? dn times dou square n prime by dou x square. N prime is what? The excess minority carrier concentration. Usually it is what? Del n, but I would use n prime. Okay. Plus G minus R. Because in the question it has been given that the semiconductor is at steady state at steady state there will be no time variation, so dou n by dou t is what? 0. Okay, so this thing, it is what? 0. So if this is 0, it means dou square n prime by dou x square. Okay, there is also dn. This will be equal to what? Minus of g minus r. Already the red graph is what? How g minus r varies with distance. If you know how g minus r varies with distance, you just have to invert this graph about the x-axis to find out how, or to plot minus of g minus r versus distance. Okay, so now let us try to sketch how this second derivative of the excess magnetic error concentration varies with distance. Okay, already we know this dou square n prime by dou x square is proportional to what? Minus of g minus r, and this red color graph is what? For g minus r versus distance. Just invert it above the x-axis. Okay, then you would get this kind of a thing. So there is what? Dou square n prime by dou x square with respect to distance. Outside minus ln to plus ln, because g minus r is what? 0. Even minus of g minus r is going to be 0. So here and here it is going to be 0. And then these two sections, just invert it, you will get something of this sort. Okay. Now from this graph, which is between the second derivative and distance, let us try to sketch how the first derivative varies with distance. Why is the first derivative important? Because it is the first derivative that will give us the actual value of the current density or the electron current density. So how do you get the first derivative from the second derivative? Is it not by way of integrating? But before we do the integration, let us get back to this observation. What was our earlier observation? That between ln and 2ln, the excess magnetic error concentration profile would be linear. Same for this range between minus ln and minus 2 ln. Now m is what? Slope. And this slope, is it not constant? Yes. And here the slope is what? Positive. I'll just write it. Minus 2 ln less than x less than minus ln m, that means what? Dou n prime by dou x. It is positive and constant. It is what? A positive constant. And similarly, between ln and 2ln, again the slope is what? Constant, but this time the slope is what? Negative. Okay. So between ln and 2ln, again the slope, that means what? Dou n prime by dou x. It is a constant, but it's a negative constant. So we'll make use of these two facts while plotting how the first derivative, that is dou n prime by dou x, varies with distance. Okay. Okay, from the second derivative, I am trying to show the variation of first derivative with respect to distance. First derivative, it means what? Dou n prime by dou x with respect to distance. See, already we know that between minus ln and minus 2ln, the slope, that means what? The value of dou n prime by dou x, it is what? A positive constant. Positive constant, it will be like this. And then between ln and 2ln, again the slope is what? Constant, but this time it is what? Negative constant. Again, because of symmetry and so on, this positive constant slope and this negative constant slope will have the same magnitude. Okay. So between ln and 2ln, you will have the same slope, but the slope is going to be negative and constant. Okay. So you know, something like this. Now what happens in between minus ln and plus ln? For that you have to integrate this second derivative. Okay. You see, up to minus ln, what is the area under the curve? It is 0. But beyond minus ln, beyond minus ln, are we not adding negative area? If you keep on adding more and more negative area, then the value of the integral, it keeps on decreasing. That means what? This will keep decreasing, okay, something like this. And then you continue to add even more negative area, and beyond ln you are not adding any new area. If you are not adding any new area, then the value of the integral will remain constant. So here also beyond ln you can see the value of dou n prime by dou x, which is the integral of this thing, has already become a constant, okay, again because of symmetry and so on. So this will decrease. So here it is what? Positive, and here it becomes what? Negative. So this is how the slope of the excess minority error concentration profile varies with distance. Now from this thing, if you want, we can also plot how the excess minority error concentration itself varies with distance. So how do you get n prime from dou n prime by dou x? Again, you just have to integrate this thing, but you have to be careful about the boundary conditions. At minus 2 ln and also at 2 ln, the value of n prime is what? 0, okay. So if you want, I can do that as well. I'll just move this up. So n prime versus x, there is what? Minus ln, there is what? Minus 2 ln, again ln, 2 ln. Already we know at the two ends of the semiconductor, the value of n prime, or the excess minority error concentration, it is what? 0. And from minus 2 ln up to minus ln, because you know n prime will linearly increase, right? So here also we have the same thing. And when you go from 2 ln to, when you go from 2 ln to ln, again it would linearly increase. In fact, these two are symmetric, okay. And then what happens in between minus ln and plus ln? Again, further you have to integrate this thing. So what happens when you integrate this first derivative or slope with respect to distance? Again, let us not worry about this range between minus 2 ln and minus ln, since for this range already we have drawn the minority error concentration profile where it varies linearly as you go from minus 2 ln up to minus ln. Now if you come back to this dou n prime by dou x variation with respect to distance, see from minus ln up to 0, are we having positive area or negative area? Clearly we have positive area. If you have positive area, or if you are adding positive area, then the value of integral, that is what? The value of n prime, it will increase, okay. Already at x equal to minus ln, it has reached a certain value starting from 0. Even beyond this, n prime will continue to increase. But you know, because this slope value is what? Decreasing, even the rate of increase of n prime, it will decrease, okay. So it sort of does this thing. And then if you look at the slope between 0 and ln, are we adding positive area or negative area? Between 0 and plus ln, clearly we are adding what? Negative area. If you are adding extra negative area, always the value of integral will start decreasing, okay. So at x equal to 0, n prime, it sort of reaches a maximum value, and thereafter n prime starts decreasing. I mean, it should, right? Because for x greater than 0, look at the slope. Is it not negative? Slope negative, it means what? The actual value, it will decrease with distance, okay. So it keeps on decreasing, again because of symmetry and so on. Whatever you have in this range, the same thing will also have between 0 and ln, okay. So you'll get something like this. So this is the final minority error concentration profile, how it varies with distance, okay. So at x equal to 0, it is what? Maximum. Again, you can observe that at x equal to 0, what is the slope of the minority error concentration profile? It is 0. If you draw a tangent, it will have 0 slope. Even our slope profile, how the slope varies with distance, at x equal to 0, its value is also 0. So it's a kind of feedback thing, okay. That's all. So here, so this is how the second derivative varies with distance, and from here we have drawn how the slope of the minority error concentration profile varies with distance. That is what the slope profile. And from here I have drawn the actual minority error concentration profile. In fact, if you want, we can find what exactly is this value n prime of 0, but that is not really required. Okay. In fact, we can also derive an expression for this complete curve. Between minus 2 ln and minus ln, is it not linear? Again, from ln to 2ln, it is what? Linear. And between minus ln and plus ln, it is what? Parabolic. It is kind of parabolic. Okay. You can get expression for each of the three segments of this complete curve, which represents what? The excess minority error concentration profile.